Yes, so this is joint work with all of these guys and was done during an internship at Samsung Research America. Right. So I'm going to start talking about the process of retrofitting type system onto previously untyped programs. So the situation is like this. There's a lot of programs out there that has already been written, and we would like them to satisfy some property. So the green area here indicates the programs that satisfy the programs. And well, because these programs were not written by us, some of them will not satisfy the property of interest at all, whereas others might almost satisfy the property and might just require a minor rewrite to be considered good. So that's a microphone. Okay, but yes, like this. Okay. 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 Right. So we would like to prove that some of these programs actually have or satisfy the property of interest. So we implement a static type system. And the first iteration of this type system is not really able to prove any programs to be good. So we take another iteration and increase the expressiveness of the type system. And we do so again, and eventually we can prove some programs, but not all of them. So ideally we would like to prove all of the programs in this light green area to be good. So we get to a situation where we might identify that there is a certain programming pattern. It's no longer a question of supporting features of the language. It's programming patterns that are actually used by programmers. Maybe if we added support for this particular program pattern, we could prove this corner of that program to be good as well. But maybe we focus on this program instead, thinking, oh, this corner should be easy to support as well. But if you look just as closely as the programmer, okay. Okay. Well, the programmer might miss, might waste a lot of time on implementing this a feature that could, a type system feature that could support this corner of the program, because really the program is not good in practice. So at this point, it's a question of which type system features are really worth implementing. And there's a lot of trade-offs in this. With the usefulness of a certain feature, how many extra programs can we actually type check, versus the implementation effort, and it's going to be hit and miss, as you just saw before. And we believe that the current approaches for doing this retrofitting, for picking the type system features to implement, are too slow because they are ad hoc. They're based on anecdotes. That's this programming pattern. I've seen that a few times. We might need to support that. But to a large extent, the approaches are slow because they're manual. Because whenever you come up with a new fancy type system feature, you might need to add type annotations to a large part of the code base all over again. And you need to do this for every iteration of this search for the right type system. So what we provide is a faster exploration of these trade-offs. And it's faster because it's automated and it provides quantitative guidance for the type system programmer. So it's not intended to replace the expert knowledge of the type system designer. It's meant as a guidance for him. So a fundamental assumption of this approach is that we can do quantitative comparisons of type systems. So in particular, if we have two type systems and one is more precise than the other, we'd expect the more precise one to produce fewer type errors. So if we count the number of type errors that occur for 3 different type system configurations, one with monomorphic functions, one with parametric polymorphism, and one with intersection types, we'd expect the intersection types to produce the least number of type errors. And from this, the implication is that choosing intersection types in your type system would probably be the right choice. You would be able to type more programs. But if you also consider the complexity of actually supporting intersection types, you might find that they are considerably more complex, and it's just not worth the few extra programs that you can type check to spend a lot of time on implementing intersection types. So the conclusion, implication here is that maybe parametric polymorphism is actually the best trade-off. Of course, being told this, once you have already implemented all three type systems and count the number of type errors, is kind of moot. So what we provide here is that we tell you that you don't need to implement all three type systems in full in order to do this approximation, because we can provide an inexpensive approximation instead, but where we approximate all three type systems. So the obvious question now is whether the approximation is good. So I'd like to jump to the evaluation part of our paper to convince you that the approximation makes sense, and then I'll explain how we actually do the approximation afterwards. So for JavaScript, we have evaluated this technique on JavaScript. Most programmers would agree that this programming pattern occurs. You do some kind of type-off test, and inside the condition, inside the if branch, you use f as a function if you tested it to be a function. So union types would be reasonable to add to support this kind of programming pattern. So if we compare two type systems, one without union types and the same type system just with union types, we can do so easily in the framework I'll present later. We can get this approximation of type errors we would get for the code base we're interested in. And concretely, we see that adding union types will reduce the number of type errors slightly. And if we peek into the more details of the experiments, we see that this reduction occurs for all of the benchmarks. So it's not just a single program that really benefits a lot from union types. So the implication here is that union type would help us, but it's not like they eliminate all the type errors. A similar experiment can be done for function types. And function types the choice of function types for JavaScript might be even more complex. You might consider, maybe we can just get by with just union types, maybe we need error geoloading, maybe we need parametric polymorphism. So the same kind of type error count for three different type systems, where the thing will vary are the function types. And again, we see that the more precise type system, the one based on intersection types for functions, produce the least number of type errors. And we see that the trend again holds across all of the benchmark. It's not just a single fluke. But implementing intersection types might be expensive. Maybe parametric polymorphism would be a better choice, but it's certainly not the complete solution. Right? I'd like to take a sneak peek at the conclusion now. So what I've presented now is that we can do these quantitative comparisons of the number of type errors, and this should guide the type system designer towards what type system feature he should really spend time on implementing, because with these graphs he'll know if he'll get any effect of actually supporting something complex. And we can approximate these type error counts, and the approximation matches our expectations for how they are from what we would expect from more expressive type systems. And as you're going to see in a moment, we can do these approximations rather inexpensively. So let's talk about the approach called the approach trace typing. And this is the approach that will in the end produce these graphs where we approximate the number of type errors for different type system configurations. And it consists of multiple steps. And I'm going to go through the steps in a moment, but you obtain a trace from a program that you run. Then you implement a type ascription operator that relates to the type system you're trying to approximate. Then you later merge variables, again in order to approximate the type system you're interested in. And then you can do type checking and get these type error counts. So the first phase is obtaining the trace. So if we to the left have a program that can be run, possibly through a unit test suite, you can see that we have an object A that's being allocated. So in the trace, that will also be represented as some object being allocated and getting a property assignment. Similarly, object B is allocated in the source code, and when run, it goes through this complex init function where the point of this talk is that it's complex. But in the trace, it will eventually be clear that all that really happens that relates to B is that b.q is assigned the string value foo. It's also a function in this program, and we invoke it twice. And the invocations of this function leads to these parts of the trace, which are very similar. So the point here is that the trace represents the dynamic behavior of the program. So the function calls are represented twice in this in the trace we generate, even though syntactically there is only one function body in the original source program. So the next phase is that we want to ascribe a type to the values of this trace. And this is in some sense what replaces the need for manual type annotations or a complex type inference. So for the A object, a reasonable type ascription is that it's an object with a p property of type integer. And this is something the type system designer provides. So an ascription operator takes value and produces a type. Similarly, for the B object, the three relevant trace statements are these three. And the conclusion is that a reasonable type is a p property of type integer and a q property of type string. For the two calls to the f function, we ascribe a type based on all of the invocations we have observed to the function. And in this case, for a monomorphic function, a type could be some object that has a p property of type integer, and it returns an integer. So this is ascription that is configurable. So if you had picked a different ascription, you would model a different type system. Right. So the next step is that we want to merge variables, because in the trace we had represented the two calls to the f function twice, because we had two calls. And all the variables in a trace are unique, such that we can later choose how we want to merge them. So after having done ascription, the type of x1 during this function call is this object with a p property of type int, whereas during the second call, the type of the x variable is a different type. But in order to approximate monomorphic functions, we might want to merge these types variables back together, and the merge of this type and that type would then become this type according to the provided type lattice. And once again, this is configurable, and a different merge strategy, for instance one that would keep the two invocations separate, or one that considered flow sensitivity or path sensitivity, would yield a different type system. So this ascription operator and the merge operator are the main things that need to be provided to the trace typing framework in order to approximate a type system. So at this point, we now have types for all the variables in the program, or in the trace rather. So if we want to type check the two calls in the trace, we do so with the type we just merged, using the variable we just merged together and used this type for. So accessing the p property on such an object, well, it type checks, but it wouldn't necessarily be the case if we had if the program was very different. And eventually, if this is done for a lot of programs, we will get to these type error counts, and then we can decide on which type system features we really want to implement. But so far it has been a really cheap approximation of different type systems. So this is not the only thing we can get from trace typing. It's not just limited to the standard object types and function types and primitive values. You can also check something different with slight modifications of the framework. For instance, there is a type system for fixed object layout at SAS last year, where a question during the design of this type system was whether programs satisfied certain properties. For instance, whether writes didn't occur to inherited properties, and using trace typing we found this to be mostly true, and in the cases it wasn't true, it was easy to rewrite the programs slightly. Two similar tests were performed whether valid prototype setups were used and whether valid field overrides occurred. So this was used to guide the design of a new type system, where the question was not, do we need this or that kind of precision, but whether the fundamental assumption of the type systems made sense. A very different thing we can extract from trace typing is type guard identifications. So JavaScript has many occurrences of this programming pattern, where some kind of type test is performed on a variable, and then the variable is used as that type inside the if branch. The question is, what are the kind of type guards that you need to support in order to have proper elimination of union types? And from that, we can extract the kinds of type guards that occur from the trace. So if we observe that x at this position is not always a string, but at a subsequent read of that variable, it is always a string, and well, no writes occur to x in between, then it is very reasonable to assume that some kind of test related to the last read of x, where the test was about the type of x, had occurred. So this would then identify this exact expression. So if so using trace typing, we extract all of these expressions where the type test occurs. We can do a manual classification of that. And for our benchmark suite, we've then found 164 of these type guards, where I think the most interesting takeaway is that of all these type guards, only 6 of them were not local. So the type test itself was syntactically present inside the condition and not having to reason about variables and their relation to a certain type test would certainly simplify a type system. Okay, so to conclude on all this, we have presented trace typing as an approach for evaluating retrofitted type systems, and we do so in a quantitative way, comparing the number of type errors, and the approach is automatic. There's no need for manual type annotations, and it's inexpensive in practice to implement different type system variants, but it comes at the cost that it's approximate. But our evaluation shows that the approximations are actually good. And lastly, it's a very flexible approach in a sense that we did 3 very different experiments with the framework. So with that, I'd like to say thank you.
Thank you for interesting talk. As far as I understood, the kind of type systems that you can check are kind of hard-coded into your tool. Is that correct?
It's yes. So the implementation itself, yes, but not the approach itself. So you have these two. There are really these two handles where if you can ascribe a type to a value as it occurred through the trace, and then later merge variables according to a different strategy, that's what you can experiment with.
Okay, so do you see any ways how to probably make a type system input so your tool can take as an input some description of type system you want to check, and then produce these rules for implementation?
But if you already have a description of the type system, a formal description, then there's no need to try an approximation of the type system.
No, I mean, so you can check, for example, simple type system, intersection types, some other types. If I want to check my untyped code against another type system which is not implemented in your tool, do you see any possible ways to make this description of desirable type system an input to your tool, or I have only implemented inside the tool, like all the checks for the? Probably I misunderstood something.
So the framework provides these two. These are two main tools where So the thing you need to provide for me is an ascription operator that, given a value, however it is occurs throughout the trace, convert that to a type in your type system. So you provide a type lattice and an ascription operator from the value to the type.
Okay, that's probably talk later. Okay.
Okay.
A very interesting talk. Thank you. I was wondering, do you think the same results would apply to another experiment where you would take a language with a very rich type system, take away then try out the various type system and see whether the interesting idioms are being used? I'm wondering that maybe because JavaScript doesn't have any, so you have found that sophisticated features like polymorphism or intersection types do not really arise in the programs.
No, I would say we've found that. So what we've shown is that
beginning of the talk, was any of that real numbers, or was those just?
I thought they were real numbers.
The word would.
These are real numbers from the evaluation.
Okay, those are.
So what are there? There are no numbers here.
Yes, no. I can go there with a ruler. Are those real?
Yes. So these are actually just the sum of these columns.
Ah, okay.
So it's the same. It's the same image.
So your point was that intersection helps, but it may be too painful.
Exactly. Yeah.
And polymorphism doesn't help particularly.
No. So this is parametric polymorphism, and we just saw for this example, right? Where if you have a function that dispatches on the number of arguments, that doesn't really fit with parametric polymorphism. So there are many different programming patterns in JavaScript because they're not restricted by the type. The program is not restricted by the type system, and parametric polymorphism is not the solution for this. Now, of course, part of this approach, we need to infer where are the type parameters in for the parametric polymorphism, and that's heuristics, but it's certainly not the case that it help in all the cases.
Right, so my question was, I do think that your slides kind of show that parametric polymorphism doesn't bias much, and I was wondering, perhaps it doesn't bias as much because it is not in the programmer's head and therefore they don't use it implicitly,
exactly.
But it would buy me a lot if I was programming in Okami, for instance.
Yes, okay. Then I think we would infer the proper parametric types. And
so which language are you going to analyze next?
I guess this is stuck for now implementation-wise on JavaScript, because obtaining the trace itself is a rather large implementation effort, but once that has been done, it's easy to experiment with different type systems.
Last question.
Oh yeah, thank you for your talk. Can you go to the slide where you have the bars for the evaluation?
For the what?
The larger one.
That one?
Yeah, that one.
Yeah.
So as I understand, a user of your system, the parameter you give them is how to merge this information.
Yes.
Are each of these different type systems implemented just through the merging, or is there more going on?
So in order to implement a type system in this framework, you need to provide the ascription operator as well, and some these type of bound operators, and then the merges for different variables. So in this case, for when we experiment with different function types, using intersection functions, way less variables would get merged than in the case where we just have monomorphic functions.
So to clarify, base, poly, and intersect are all just variations on those two parameters?
Yes.
Okay, thank you.